Our next finalist I'm welcoming is actually a team effort, and it's led and presented by Dr. Aissatou Ndiaye. She's a climate scientist and a postdoc at the chair for regional climate and hydrology at the University of Augsburg. She has obtained a PhD of the University of Abdu Mumuni of Nigeria. Her research focuses on promoting solar energy integration. She represents a team effort today, and the team is joined by 4 researchers from the climate and energy sector, namely Dr. Victoire Gafi Kondi Akara, a group leader at the African Institute for Mathematical Sciences Research and Innovation Center in Rwanda, Oluwatimi Delano Thierry Odu, coordinator of SPS Blue Nile project at the Karlsruhe Institute for Technology in Germany, Dr. Dahiru Wayne, a postdoc at University Sheikh Anta Diop of Dhaka in Senegal, and last but not least, Dr. Windmanakata Savadogo, who's here today to join Dr. Ndiaye during the Q&A. So welcome. The 5 researchers today aim to build a high-resolution climate data set for West Africa using a transparent, open access and collaborative approach. Dr. Ndiaye, we can't wait to hear more from it.
Thank you very much for the introduction, and thank you for giving us the opportunity to present our project. Good afternoon, everyone. I will take you through our proposal, which is about high-resolution climate data set for West Africa, a service for climate protection and energy transition. So West Africa is currently facing several challenges, and the first challenge is the rapid increase in its population, which is expected to double by 2050, with the highest density over the continent as compared to other regions. And the second challenge is access to electricity and clean energy for cooking. West Africa is one of the regions with the lowest access to electricity, with more than 160 million people without access to electricity, but also around 1/3 of sub-Saharan Africa without access to clean cooking. So the SDG 7 goal, which is access to energy for all by 2030, might not be achieved in this region. And beside this comes the vulnerability to climate change. West Africa is very vulnerable to climate extreme due to its low adaptive capacity. So the temperature is increasing over the region, over the continent, but also energy infrastructures are vulnerable to climate variability and change. So high quality data is necessary to strengthen adaptive capacity, but also to plan mitigation action for resilient and sustainable development. High quality data will optimize solar and wind installation, but also it will expand access to clean energy to support the SDG 7 goal. However, this high quality data is scarce in West Africa, mainly due to a sparse network of climate stations with no high quality data available for short and long-term planning. So in this map of IPCC, it shows the station that was still active in 2017. And over this graph, we have the declining trend of the number of stations from 1990 to 2020 over the region. So high quality climate modeling is needed to generate improved climate data set for West Africa. And for this, we have physical-based model, but we also have statistical approaches with AI machine learning. However, this latter requires a lot of data to train the model, and this kind of data is not available over the region. So our approach we will use a physical-based model to provide or to generate a high-resolution climate data set for West Africa. And this will support climate protection policies and energy transition through policy support, solar and wind energy, emission reduction, energy storage, but also sustainable development. So in this slide, we show a comparison between a global climate model at coarse resolution, 100 kilometers, and the one that has been downscaled to 15 kilometers, which is a high resolution. And this is just a text case example that we have been run in our HPC over this region. But in our project, we will still go down to 3 kilometers. And we can see that there is a big difference between the two maps, with the one at high resolution here on the right, showing much more details are compared to the one at coarse resolution here. So with the help of this Einstein award, we plan to generate a first of its kind detailed spatial temporal climate data set for West Africa as climate services that can be used by many sectors, including the energy sector. We will also provide information on the projected renewable energy production based on a cutting-edge regional climate model at 3 kilometers spatial resolution for detailed planning analysis. And we will develop an open access data set and also a modeling framework hosted on GitHub to facilitate transparency, collaboration, reproducibility, but also model development in West Africa. So this figure summarizes the workflow of our M1. We start from the left where we have to collect data, global climate data from SEMIP6 and aerosol information. And this data is going to fit into our regional climate model. And the simulation is going to run for the historical period, but also in the future under different scenarios. The low emission scenario, which is SSP1 2.6, and the high emission scenario, which is SSP5 8.6. And the output of the model will undergo quality control and validation and will be integrated into an open access data set ready for use over West Africa. So this is a method at a glance for this M1, where we have to use information from global climate model, information about wind component, temperature, humidity, pressure. And we will use this information to force our regional climate model and downscale this global climate model to a high resolution, which is 3 kilometers. And we will run the simulation in the historical period, which is from 1981 to 2014, but also in the future from 2015 to 2100. And the output of the model will provide impact about energy planning, but also climate impact assessment. So why do we choose this model, this regional climate model? We chose it because we already have expertise in the team with papers already published in international journal. But also this model provides flexibility to integrate aerosol information, which is very important in our case because of this region, West Africa, proximity to Sahara dust, which is a source of, to Sahara Desert, which is a source of dust. So our M2 consists of taking output from our M1, which is the high resolution climate data. And this is going to be for renewable energy assessment and renewable energy production for West Africa to support planning. And in our M3 now, we will develop an open modeling framework, which will bring together all the components of our work in a collaborative and transparent way. So this modeling framework can be shared, reused, replicated, but also adapted to other regions. And this openness will help or will support reproducibility by researchers, collaboration with local and regional partners, transparency, but also interdisciplinary across institutions. So to run this project, we have access to the Kashué Institute of Technology, HPC, which we have been using for our simulations. And this HPC has a large total capacity of 2.3 petabytes. And in addition to this, we also have access to the HPC of Leibniz Supercomputing Center of the Bavarian Academy of Science and Humanities. And at the end of this project, we expect to deliver and improve climate services with different parameters that can be used by many sectors. We will also provide indices, solar energy indices and wind energy indices, public data, open science through the modeling framework, empowerment of local researchers, but also policymakers. And all of this will inform decision-making for a resilient West Africa. And this project has a regional and global relevance because it's the first 3 kilometers climate data set for West Africa. So it will support climate adaptation, energy transition, and also resilience planning. And it will also contribute to the global climate goals, which is the SDG 7, which is about access to electricity, but also the 13, which is emission reduction. The project will also have scientific and technical significance through research publication, but also through the modeling framework, which is reproducible, and the innovative method enhancement. The project will also have societal and policy impact, but also it will have capacity building and knowledge transfer through empowering local researchers and institutions, but also strengthening collaboration. So this is the theme behind this proposal with our respective institutions. So I thank you very much for your attention, and we are ready to take any questions.